Okay, one more example from this section on implicit derivatives, very similar to the one we did actually in the beginning. They give us an equation, okay, and they ask us to compute dy dx, differentiating implicitly, and then evaluate that derivative at this particular point. Okay. Now, in order for this calculation to mean anything, that point should satisfy this equation. Because this equation, I have no idea what it looks like if we were to graph it. It's probably pretty complicated and something we don't see very often, but it's some kind of a curve, and this point should be on the curve. And indeed, if you put 1 in for x and y, both sides of the equation are equal, so 1, 1 is on this curve. Okay. So what's the slope of the curve at that point? Okay. Well, that's where we need to compute the implicit derivative. So I take d dx of the left side and set that equal to d dx of the right side. Okay. And again, not too bad. We're going to have to use a product rule over here, it looks like. But in fact, first of all, right away I can I can start using some of my basic rules. This is the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed. Okay. And over here I've got 2 times the derivative of xy. Okay. So remember I factor that 2 outside. Okay. Well, just use the rules we've got. The derivative of x cubed, the power rule, we get 3x squared. The derivative of y cubed with respect to x, we have to use the generalized power rule because the variables are different here. So we're treating y as a function of x. So we get 3y squared times the derivative of y. Okay. There's one of those dy dx's we're going to have to solve for. Okay. Now over here, excuse me, we've got 2 times the derivative of xy. Well, got to use the product rule there. Okay. And the book says, the product rule, we've got an f and a g, a first function and a second function. We take the second function, y, times the derivative of the first, and the derivative of x with respect to x is 1, okay, plus the first function times the derivative of the second. Okay, the derivative of y with respect to x is just dy dx. Okay. So if you look at what we have here, maybe I'll just write it one more time. 3x squared plus 3y squared dy dx equals 2y plus 2x dy dx. Okay. Okay, we've computed the derivative implicitly. We just need to solve for that symbol dy dx. Okay. So I've got 2 terms that have a dy dx in them. I need to move those over to the same side of the equation and move everything else over to the other side. So what I would do in this problem is from both sides I would subtract 3x squared. Okay, that'll get the x term, the terms without a dy dx on one side. And then over here I'm going to subtract the 2x dy dx to get the terms that do have a dy dx factor on the other side. Okay. So what I'll end up with is something like 3y squared dy dx minus 2x dy dx equals 2y minus 3x squared. Okay. So since both of these terms have a factor of dy dx, I can just factor it out of both, and I'll go ahead and do that kind of in line here to save some writing. And to get dy dx by itself, I just need to divide this over to the other side. And I would get dy dx equals 2y minus 3x squared. And remember, I'm dividing this over to the other side. So over 3y squared minus 2x. Okay, excuse me. Okay, so that's the derivative of y with respect to x. It's, as usual, an expression involving both x and y, since we're doing an implicit derivative. But we're asked to find this slope at the point 1, 1. So this is sort of the part A, but at the point 1, 1, well, we can figure out what the slope's going to be. We can just put 1 in for x and 1 in for y. So we get 2 times 1 minus 3 times 1 squared over 3 times 1 squared minus 2 times 1. This looks like this is going to be negative, let's see, 2 minus 3, so negative 1, 3 minus 2, which is 1. So negative 1. Okay. So regardless of what this curve looks like, this original equation we started with, at the point 1, 1, which is on the curve, the tangent line has a slope of negative 1. Okay, so that's what we've gained from computing this implicit derivative.